today. I am Asma LADJEROUD, PhD student of Dynamical Systems and Applications at the University of Sheikh Zayed. My supervisor is Professor Asma LADJEROUD. So today we're going to talk about the chaotic behavior in certain family of piecewise smooth maps. And the main purpose of this presentation is to discuss the different scenarios of border collision bifurcations and give an idea of structural proof for the existence of a special type of chaotic behavior in certain family of piecewise smooth mappings. So the first section is going to be a kind of an introduction. Chaotic systems are dynamical systems that exhibit unpredictable and seemingly random behavior despite of being governed by deterministic laws. They are highly sensitive to initial conditions, which mean that small perturbations can lead to vastly different outcomes. There are several chaotic systems, known chaotic systems, such as Lorentz, Anon, Russler, and lossy attractors. So we cannot talk about chaotic behavior without mentioning the notion of an attractor or a strange attractor. So an attractor is the asymptotic limit of the solutions starting from any initial condition located in a pattern of attraction, which is a domain of non-zero volume, while the strange attractors are ideal concepts occurring in chaotic systems satisfying a number of rigorous mathematical properties. Actually, in the current literature, several dynamical systems are chaotic deterministic and have at least a strange attractor. Sometimes it is hidden and sometimes it shows itself. The strange attractors are classified into three principal classes, which are, the first one is hyperbolic attractors. One of the most examples for this case is the Arnold-Cat map, defined as follows. The second type is Lorentz type attractors, and the most known example of this type is the Lorentz system, defined as follows. The third one is the most complicated type, is the quasi-hyperbolic attractors, and we will give an example for it in the next pages. So, a piecewise smooth map is a mathematical function which is defined on a discrete domain. It is composed of pieces or regions that are joined together in a manner that is smooth at the boundaries. Actually, piecewise smooth maps can exhibit chaotic behavior and they can be studied using the Banerjee's normal form of border collision. The following map F is a one-dimensional piecewise smooth map defined on R and depends smoothly on the bifurcation parameter mu, where xb is the border which divides the state space into two regions, the right side and the left side. Actually, the one-dimensional smooth maps normal form was provided by Yuan in 1997 and Banerjee in 2000, while the two-dimensional piecewise maps normal form was provided by Banerjee and Gribouji in their paper The Collision Bifurcation in Two-Dimensional Piecewise Smooth Maps in 1999. It is kind of a lossy map generalization, which is called the border collision normal form, and it is given by the following system, where the GK is the Jacobian matrix. The parameters K and delta K are taken to be fixed, and mu is the parameter bifurcation, of course. The fixed points of the system in the two sides, the right side and the left side, are given by x and y. The stability is determined by the eigenvalues lambda 1 and lambda 2 defined as below. So, going to the possible types of fixed points of the normal form given in system 3, the border collision normal form. So we have two cases. The first one is when the Jacobian matrix is positive. So the fixed point, it varies between regular attractor, regular saddle, flip attractor, flip saddle to clockwise spiral and counterclockwise spiral. In the second case, when the determinant of the Jacobian matrix is negative, the fixed point varies between flip attractor and flip saddle. The instance in which a locally unique fixed point before the border gives rise to either a new locally unique fixed point or locally unique period to attractor after the border, with no occurrence of chaos, are well documented, of course. These regions are called regions for non-chaos. They are classified in four cases, depends on the sign of the determinants on both sides of the system. 3. They will be illustrated using schemas where we have 6 essential scenarios. Some of those scenarios have secondary scenarios to discuss. The first scenario is when we have positive determinants on both sides. So we have the scenario A and B, where B is divided into two scenarios, B1 and B2. The second case where we have a negative determinants on both sides, so it's divided into two scenarios C and D. The third case, when we have a negative determinant to the left and a positive determinant to the right, we have only one scenario, which is divided to two scenarios, E1 and E2. The last case, when we have positive determinants to the left and negative determinants to the right, we have also one scenario divided to two scenarios, F1 and F2. So let's go to the quasi-hyperbolic regime, which is the special type of chaotic behavior we will discuss today. Let us consider a new mapping system which has some resemblance with the border collision normal form. It is defined as follow, where F is divided into two maps, F small f and G. This system has a single fixed point, which is y. Its stability is determined by the eigenvalues values lambda 1 equals alpha and lambda 2 equal minus delta k. So we're gonna we'll have to use this theorem to determine sufficient conditions for hyperbolicity. It says that if we have a C1 map defined on an open convex subset U, and this map is divided into two other maps, then if the fourth conditions are occurred, we can say that any compact invariant set in this open subset is hyperbolic, and also we have some properties about the stable and unstable subspaces. So, by applying this theorem of the new mapping system, which has some resemblance with the border collision normal form, we have the hyperbolicity condition defined as follow. And due to this condition, we can say that our fixed point is settled in the both sides, while the determinant of the Jacobian is negative. Now we want to find an absorbing region and find necessary conditions for its existence. For that, we need to use this theorem. It is called the theorem of Shinnikov and Gavrilov about hyperbolicity and the quasi-hyperbolic attractor. So I will give just an idea for the proof. It took a lot of time. It takes a lot of time. So the idea to apply this theorem to our system, the idea of the proof is as follows. We'll define a domain omega we'll consider 4 points A, B, C, and D, where 2 points are in the right side and the other points are in the left side. And then the first step is to prove that the points A, B, C, D are in omega. The second step will prove that the images of the points A, B, C, D by our formula is still in omega. The third step is to prove that or to find the necessary conditions for which gives that the images of the lines AB, BC, AD, and DC are still in omega. And as a last step, we will prove that for any point x, y in omega, the image of this point by our formula will be in omega. So as a conclusion, the main analysis of proving the existence of a quasi-hyperbolic attractor for the new map, which is a particular family of 2D piecewise smooth mappings, is based on finding an absorber region and then proving that it contains a quasi-hyperbolic attractor for the form under some specific conditions. Here are some references. The last part of this presentation took part of a published work titled on the quasi-hyperbolic regime in certain family of 2D piecewise linear maps and the direction of the Professor Asma LADJEROUD. Thank you so much.